Everyone, welcome to week 5. I'm going to run through the coding guide of this week, just like I did for week 4, working with spatial vector data. And I'm literally just going to go through the same stuff. This is an optional video. You don't have to watch it. It might be helpful as I go through and explain some things. But feel free to skip through it if there's a single portion of this that you're interested into. But yeah, thanks for tuning in. So I'm just going to cover introduction to spatial raster data using the Terra package. So this is the fun stuff. If you remember from the week 4 lecture guide, spatial raster data consists of cells that are of equal width and length. These cells contain values that are either numerical or continuous or discrete and categorical in nature. So each cell, same length and width. And these cells contain information. And that information can give you insight into what you're looking to. And they represent natural features on Earth, like elevation, aspect, slope, land cover, kind of whatever you want. Soil properties, things like that. And they come generally in the form of TIFF files, because that's just what they are. Sorry, I got a text message. But anyway, so TIFF files. And so that's .tif or .tiff files. And we will be working with these for the majority of class and possibly all of it. But we might have some introduction to a few other, like .img and .hdr files. These can both represent raster data, as they do. But TIFF stands for tagged image format or tagged image file format. And, don't really need to dive too deep into this, but that's what they're generally called. So if you see a .tiff file, right away you can understand that this is a raster data. Now, raster has a resolution associated with it that differs from spatial vector data. And that really refers to the spatial resolution is what it's called. And that means pixel size. So pixel size would be cell size. The data we're working with in this coding guide is either 30 meters, so 30 meters in length and 30 meters in width, or 1 kilometer in length and width. And below, here's just 4 images of the same exact area, same exact extent, but with different pixel sizes. So you can see if it's 8 meter pixels, it is far more coarse, whereas you go to 1 meter pixels, that's looking like some high resolution imagery. So resolution plays a lot into what you can do with your data, what information you can gather from either imagery or digital elevation models, things like that. And it also correlates to either availability or price. So there's some imagery data sets that are 1 kilometer in resolution. And so that's really, really coarse. And so you can kind of get an idea of what that might be used for. You might use something of that size for maybe a global study. So global forest cover loss, something like that. And the lower the resolution it is, generally, the higher availability it is, and the higher availability it is for the whole world. Whereas when you get down to 1 meter or sub-meter pixel levels, that tends to be pricier, tends to be harder to get to, and tends to have a lower covered extent. It's generally 1 meter for the whole world, could be pricey. And then when you're getting down to they have centimeter-sized pixels. That stuff's just crazy. It's costly, but it's really cool if you can get it. And we'll talk a bit more of that next week in remote sensing. But yeah, for right now, if you are unfamiliar with raster data, the bigger the pixel size, the coarser the image, the smaller the pixel size, the finer the image. Terra. So straight from the Terra R documentation, Terra provides methods to manipulate geographic spatial data in raster and vector format. Raster data can divide space. Raster data divides space into rectangular cells, the pixels we were talking about, and they are commonly used to represent spatial continuous phenomena, such as elevation or weather. We also covered that they can be discrete meaning that they have categorical values within their cells. Satellite images also have this data structure, so this will be a good intro to next week's, which is remote sensing. In contrast, vector spatial data, points, lines, polygons, are typically used to represent discrete spatial entities such as a road, country, or a bus stop, and we covered that last week. So this flows really well, going from spatial vector data to learning about rasters to learning about remote sensing and imagery. And so we're going to be using Terra in this lecture. Terra, like we covered last week, it's not specifically designed to just use raster data. It can use raster and vectors. So if you become familiar with Terra, it may offer the best bang for your buck in terms of just using one library. Having all of your functions in one package could be helpful. It's kind of a one-stop shop. And so we're going to cover some of the types briefly because for some reason the person that invented it, which is Robert Hymans at UC Davis, he is the creator and curator of the Terra package. He calls vector and raster data spat vector or spat raster. And so that just stands for spatial. So spatial vector, spatial raster. And some of the functions that require both raster and vector data using Terra, they can't just be loaded in through the SF package, which would create an SF object. They need to be loaded in through Terra and created as a spat vector. And so spat vectors function the same way as vector data does, maybe out of the SF package when you load it in. But it is simply a different data type that your SF vectors, and sometimes it requires, like I said, it's required for data analysis. Spatial vector or spatial rasters. So spat rasters support handling large raster files that cannot be loaded into memory. Local, focal, zonal, and global raster operations, polygon, line, and point to raster conversion. Basically, it's the same thing as a raster, but they're called spat rasters, and they do differ in terms of what functions you can run with them. So that's what you need to know. Good enough. Data. So Zion National Park is my favorite national park, mostly because I think I visited it as a child living in Arizona. It was very cool to see the Red Rock. I'm interested in just everything about it. It's a beautiful place. And in this coding guide, we're going to be working with raster and vector data provided by the National Park Service of Zion National Park. And if you're interested, you can get spatial data of national parks, forests, and monuments from data.gov. I will provide that link in this week's module because that could be very important as your assignment refers to your favorite national park or just a national park you pick. So the boundaries of every national park monument area under the specific agency jurisdiction is provided in the data folder. And so I'm giving you a polygon of all of the national parks, monuments, and area boundaries. And we're just going to call that nps_boundary.shape. That is in the data folder for module 5. So we are loading this in. And we're just going to use the SF package for now. We actually don't need it to be a spat vector yet, but I'm just showing you how we could change that later. So just calling it nps, sf, stread, your drive, mine specifically here, and then navigate to that nps boundary shapefile. And then if you remember from week 4, this is our information about it. So right now it's a NAT83. Looks like we're working with latitude and longitude. It is a multi-polygon dimension XY and has 427 features over 15 fields. So that would be, where did it go? That would be 427 columns over 15 fields. And this is how it looks. So right now it's very small, but you can see the United States up into Alaska, Hawaii. I have no idea. Somewhere in the Pacific. Maybe the Bahamas over here and then something over here. But they're included in the data set. So there are 15 fields describing our data, and there are 427 specific parks, monuments, or areas under management of the National Park Service. And that can be seen here, just by plotting with the $ geometry, a lot of polygons, very true. So the objective is this, we're just going to walk through basic raster analysis using the Terra package, and by the end of this, you'll have a firm grasp on how to load, manipulate, analyze, and visualize raster data. We're not covering too much into the visualization part other than just normal plots. We're going to be covering cartography a little bit more after week 6, after the remote sensing in week 7. So, libraries, as you follow along, you will need to download or install Terra, SF, and the Tidyverse. If you remember, Tidyverse covers dplyr, ggplot2, a lot of the data science packages all in one. Projections. Now, if you remember, data can be projected in different ways, and that depends on a geographic coordinate system, and a coordinate reference system, CRS, and that is just a mathematical abstract of reality. So how are we viewing the Earth? How are we either minimizing distortion or creating distortion by projecting the way our shapefiles, rasters look? So I am particularly interested in using the North American Datum 1983 Albers equal area, and that is one of my favorites. Especially working in this area, you can somewhat get the curvature of the Earth, and I think it minimizes distortion. So if you remember from week 4, we used EPSG codes. This week we're doing things a little bit differently, and when you work with this, you can just copy and paste it into your own R, like so. But it's called the proj for string information. And so essentially it's a sentence long plus there's like proj AEA plus latitude plus latitude plus latitude plus longitude plus x plus y plus ellipsoid. And so there's a lot of information in here, but it's the same way of defining a projection, and you can assign it to a variable, which I did here, proj AEA and 83. To stand for NAD 83 Albers equal area. Great, so that's just one way of looking at projections. We're going to be using this specific projection, assigning it to a variable, and you'll see how that works later. So, moving into Terra. Just like the vector coding guide of last week, we're going to go through a bunch of functions, and I'm going to open this up and you can see how many. 1, 2, 3, 4, 5, 6, a bunch of them. And so I'm just going to go through the beginnings of how to load it, how to look at your data, and then we'll get into how to manipulate it, things like that. So the very first function you need to know when working with raster data in the Terra package is rast. Couldn't have added the ER on there, they just wanted rast. So the rast function stands for raster, and it is the method of loading raster data into R using the Terra package. So it goes as follows. So you'll assign a variable, and you'll call the rast function, and you'll have your pathway, and you will have your raster.tiff. And so this, right now, we're going to load into one of our digital elevation models. We'll cover what a digital elevation model is. I don't think I covered it up here. Nope. So, digital elevation model is just a raster data, and the pixels, the cells, contain information about elevation. And if you look at it, you can see how the topography looks across the landscape. So right now, we're going to load in Zion B, and this is in your data folder. Oh, check it out. Note, right in front of me. A digital elevation model is a raster data set that contains elevation information in each pixel. It is one of the most common raster data types you'll encounter. You know, I wrote this, and I don't even remember what I put sometimes because it was right there. But covered it twice. There you go. Kind of a good idea. And once you see the plots, you'll get a good understanding of what those are if you're not familiar with DEMs. Here's the code. So Zion B, we're just going to call that. We're going to do Terra, rast. And so I believe I've covered this. Sometimes I put the entire package and then I do 2 colon spaces. You can do that without doing library Terra, without actually loading the package. I always do it just in case the package wasn't loaded, and it's just become a force of habit for me, as sometimes you'll be working with functions that have the same name, but they're from 2 different packages. So you might think you're working with one function, and for some reason your analysis is not running. So always calling that package, for example, Terra, : then the function, I always know where I'm directed to. So anyways, Terra, rast, navigating it to Zion B, and TIFF. And that will load it right in. Summary. is a function that provides a quick summary of the data by providing the basic descriptive statistics of the data set. Since we're working with elevation in meters, we should see values in the 1000s for National Park, because that's the base elevation of Zion National Park is around 1,000 meters. So, if we run Terra summary Zion B, we will see the minimum first quartile, median, mean, third quartile, and the maximum value of our cells. So you can see 1,171 is the lowest elevation in Zion National Park in terms of 30-meter pixels, and the max would be 3,387. So there's quite the range of elevations and features in Zion National Park. Frequency, FREQ, F-R-E-Q, stands for frequency. This data can get overwhelming as it is an equivalent of the function table. It will return the count of cells that contain a given value, and that's a lot of information. So how many cells does our raster data have? A lot. And so it'll tell us. So how many cells count to have the value of 1158? Perfect. 2. And then so on. And this will go for each individual pixel, and it can get a lot. So I just ran the code head to look at the first 5, which would be head, Terra, frequency, Zion B, 5. So we're looking at the first 5 of value and how many cells there are. And this can be useful for a number of reasons, and I encourage you to find that out for yourself. A histogram provides the same information as the frequency, just in a visual and less overwhelming manner. And so there is a warning when you run Terra hist Zion B. It says a sample of 8% of the cells was used. Just because we're working with a large data set with a lot of cells, it resampled just to 8%. So a model of all of the cells, but you can kind of get an idea of how the elevation may appear in Zion National Park. So you'll have a lot here in the base. And then as you go to higher elevations, there are less and less peaks that contain elevations up near 3,300 meters. Perfect. Now those are useful, but by far the most useful when working with raster data is plot. And so, as I mentioned before, you're very familiar with the plot function, but that's a base R function, not specifically just a Terra function. So when we're working with spat rasters in the Terra package, you need to be sure you are using the plot function of the Terra package. Plot from the base R package will not work on spat rasters. Very important. Wow. One easy way to make sure you're calling or using the right function is to call the package by 2 colons, like so. Terra plot raster. Covered that twice now. I often call a package before using a specific function to be sure of what I'm doing. Am I doing the right thing? And so I just keep covering the same thing over and over again. I don't remember where I put things, but yes, that is one way to do it. And then as we plot, we have Zion B, and check it out. Beautiful. So this covers an entire degree in latitude and longitude, and an entire degree north of latitude. And so we can look at how this data is reflected from our histograms and summaries onto a visual representation of reality. So you can see in these higher values, these higher greens, you have up there around 9,000 feet or so. And you can dive down in here to about 3,000 feet in southern Utah. So you can get an idea that these are mountain ranges we're looking at. You can even see the dendritic pattern of watersheds, streams, things like that. And if you look over here, if you're familiar with Zion National Park, this might look familiar. So the narrows, essentially slot canyons, have lower elevations surrounded by essentially they're canyons carved out by water. So if you're familiar with Zion National Park, this will look familiar as right above it you have very high mountain ranges, and below it you have lower upland deserts. So now this is in not my preferred projection, or CRS. So I want to use what essentially was the equivalent of ST transform for vector data out of the SF package, but it's called project. So Terra project, I'm calling it Zion B still. I'm going to put in Zion B, so the original, and I'm going to project it to my proj for string Albers equal area of North 83, which was, ta-da, right here. And as I save this information into a variable, I can just call the variable as I want to transform it. So you run the transformation and you plot it, and check it out. We are no longer using latitude and longitude, we're in meters. And we are slightly curved, as this projection takes into account the curvature of the Earth. Now, Zion National Park is this extent here in black. Pretty interesting looking extent. But our raster data currently doesn't cover the entire extent. So we need to use what's called mosaic. Now, mosaic is very similar to merging vector data, but it's only with rasters. So 2 or more overlapping or touching raster data can be combined into a single raster, and that can be extremely useful for situations like this. We want to conduct an analysis using raster data of Zion National Park, but we have 2 separate overlapping rasters, or we will need another raster to complete the area of the park. And so we don't want to be working with 2 separate raster data all the time. If we were running one analysis, we'd have to apply them to each one, and they may not match up. So basically, we just need to combine them. So I'm going to show you the code of how I got the raster of just the Zion National Park boundary, and then how to use 2 different raster data and combine them into one data. So, like we looked at before, NPS is the shapefile containing all of the protected areas by the National Park Service for North America and beyond. So we need to subset this down into Zion National Park. And so there's a column in the NPS shapefile called park name. So looking back on week 2, for data wrangling, we are going to use a function called filter. We're going to use our piping from the NPS package using filter. Column park name, we just want that to be Zion. And if you wanted to, you could search through that shapefile and look at the column of park name and see what other park names there are and how they're structured. Right now, it's just the first letter capitalized. Sometimes data is wonky and they can all be capitalized, things like that. So we are just selecting park name Zion, and then we're going to transform it to our projection. Same thing, we don't necessarily need the EPSG code because we have the information. So we have filtered and we have transformed. We have plotted our DEM. And look how I just ran plot this time, right? Nice. You just got to be sure it's using the Terra package instead. And as you type in plot, it'll give you several different options. Just select the one that's referring to Terra. And then we are running plot, which doesn't need the Terra plot. Zion bounds, geometry, and adding equals true. So we're plotting that boundary on top. And yes, you can plot raster data with SF objects. So we have a spat raster and an SF object here. So they work together. So what was the problem? We need information over here in rasters to cover the rest of our part. So here's the other side. This one's called Zion A. And we have that data in our data folder. And so that's great. We do the same thing. We plot it. So the problem is they both cover Zion. Here's Zion A and Zion B. But we need them to be 1. So we need to combine A and B. And it's pretty simple code. Mosaic. So I'm just going to call this mosaic underscore R for raster. Calling the mosaic function. And then if they are in the same coordinate system, if they are the same spatial resolution, so same cell size, and they overlap or touch, we can make a mosaic of them and make them one data set. And so here is it plotted below with our function. So this warning is saying rasters did not align and were resampled. Sometimes they overlap, and it doesn't know specifically where to draw the boundary. So it'll take the two cells and create a mean average of those cells and then stitch them together. So essentially it's the same exact information. But right now, instead of plotting A and B, we are just plotting mosaic R, run from up here, and then our boundary. And here we go. So now this is mosaic R plotted with our Zion boundary. Pretty sweet. So you can do that with a number of data sets as long as they're the same coordinate reference system and the same spatial resolution. So this is a lot of information. We're just looking at Zion. We don't want that. So if you remember, there was crop, ST crop and ST intersection from the SF package. Terra kind of does a similar thing. We only need the information for our park. And both crop and mask perform this action, but slightly different. So let's take a look at what we're doing. Now, we are cropping, masking, essentially just trimming down the size of the raster, trimming down that raster by a vector data. Currently, our Zion boundary was loaded through the SF package and is an SF object. But for this function to work, and both of these functions to work, the SF object must become a spat vector. We can change that using the as function. Let's see how that works. Okay, so Zion bounds was our SF object, but now we're going to do Zion underscore bounds underscore V for vector, and we're going to use the as function. So let's see how that works. It goes as, calling the SF object Zion bounds, and then comma, in quotations, we're putting what we want it to become. So SF objects can easily shift over to spat vectors. They don't need to change much in terms of their data structuring. It literally just changes the name of what they are. So now Zion bounds V is the spat vector version of Zion bounds just by using the as function. And that's pretty awesome. But now we're going to look at crop and see what crop does. So now we're just creating one called Zion. We're running Terra crop mosaic R, which was this larger DEM, called by Zion bounds V, our spat vector version of the boundary of Zion, and we run it. And then we are plotting just Zion and saying this is what the crop output looks like, and we are plotting the boundaries, and check it out. We have successfully narrowed down our data to a surrounding rectangle that is created by the furthermost ranges of the data set, the park boundaries, from north, south, east, and west. And so you can see here, all the cells were kept that make up that rectangle that touches the furthermost portions of each direction of that park boundary. So that's what crop does. And crop can be useful. Maybe you need the surrounding area. It really depends on what you're doing. For this one, I want things trimmed down, so I'm going to take a look at mask. And check it out. Mask runs the same way as crop, but instead of crop, I'm just putting in mask. So Zion M is what I'm calling it, Zion mask, is Terra mask Zion. So calling this DEM right here, the smaller one, and the spat vector Zion bounds V. And it crops it, well, it technically masks it, gotta be careful with your verbiage, to the extent of the spatial output of the Zion National Park boundary. We can plot it and plot the geometry around it, and since it was transparent in the middle and just has the boundaries, we're just going to be adding that around. It gives it a nice little edge to the park. So there you go. We went from having two different rasters to one big raster, and now we clipped it down to the size of ours. So you can see how this could be useful when doing analysis just on a specific area. Now that we have our extent of our digital elevation model, and you can see here, it's pretty awesome. You can see most of you have visited Zion National Park and probably didn't go farther than this extent right here. So this is the road, and then you go into the Narrows, and you can see Angel's Landing right here, somewhere up here. But Zion National Park is actually pretty big. Pretty cool area. But we want to create other spatial outputs. Digital elevation is awesome. It's used in a lot of different things. You'll see when we work with species distribution modeling that we will use a digital elevation model inside of our data. However, there's many more things you can do with raster data. So this is used through the terrain function. So terrain allows you to compute terrain characteristics from a digital elevation model. These characteristics are useful to have when examining a landscape, and you will specify which characteristic you want to calculate in quotation marks with inside the terrain function. So let's see how that looks first, and then we'll talk about slope. So we are going to be creating a slope measurement of the landscape, and I'm just going to call that SLP, shortened for slope. But this is how it works. You do Terra, or you don't need to. The terrain function, you call your digital elevation model, which was Zion M from up here, and then in quotation marks, I want to compute the slope. So slope measures the, well, slope. Slope is the angle of a slope. I think that's spelled wrong. There should not be the E. There we go. This isn't an English class. Slope is the angle of a sloping hill or cliff face and is provided in units between 0 and 90 degrees. 90 degrees being a straight up cliff, while 0 degrees is flat ground, if any of you are from, like, Kansas. So if you've been to Zion National Park, and if you haven't, you must go. I'll even give you extra credit. Not that none of you need it. You're all doing great, and this shouldn't be a difficult class. So if you've been there, you've seen the sandstone cliffs. So in your mind, how would slope look? So you're probably going to have a lot of flat areas. Then you're going to have some of those, sloping hills up to the cliffs of fallen rock and dirt and soils and some vegetation. And then there's just these massive cliffs that are amazing. So your slope output is probably going to show a lot of cells that have degree values between 80 and 90. So, computing slope as we ran through. I'm calling it slope, running the terrain function, using my digital elevation model, and I want slope. Then I'm plotting it and plotting the bounds. So check it out. You can see up here, we don't have quite 90. I bet there's a 90-degree face in here somewhere, but these are abstractions of reality, so maybe it's not perfect. But up here in the green are your cliffs. You can see how the landscape works. You have these massive cliffs. That's what makes Zion National Park so wonderful. And so you can see dark green, really steep, towards the white values, which are very flat. And so this is why a lot of people visit just where I'm hovering my mouse, because that's where the road goes through, and you can take a look at these amazing cliffs without actually having to really do much. So that's one thing that you can use. Slope is used in a lot of studies. Maybe you're looking at landslides. You would want to know the slope. Maybe you're looking at nesting birds that prefer a certain slope of cliff. There you go. So it has its uses. Aspect. Now, aspect refers to the direction of the slope face and which direction it's facing. The output is measured in 360 degrees, with north being values of 0 and 360, east being 90, south being 180, and west being 270. So, it literally is just saying, what direction is the slope facing? I'm going to give it a value based on 360 degrees. So, all of our north-facing slopes, and so the dark green here is actually pointing upward. It's facing that direction. You're going to see in the dark green, whereas you do full circle, you get down to the whites again. But if you get to like 180 in the yellows, you'll see these are your south-facing slopes, or south-facing cliffs. So aspect is also very important. So looking at snowmelt, you're going to get snowmelt during certain times of the year from certain aspects. You're going to, you can compute watersheds from aspects, seeing which way the water is going to be running as snow melts, things like that. So, slope and aspect are very common in spatial analysis studies. TPI. TPI stands for Topographic Position Index, and it's an algorithm that is increasingly used to measure topographic slope positions and to automate landform classifications. So, if you look closely, and you're going to need to look really closely, because Zion National Park, while a big area, is not that big compared to landscape studies. You can see the general landscapes of Zion being broken up into sub-landscape types. So it's the same idea as before, TPI, terrain. Using our digital elevation model, we want to compute TPI, all caps, and then we plot it. So if you get up close here, you can see there are lighter values on top of the cliff faces, and you can kind of see the outline of the cliffs and how it looks. So this is just breaking, based upon values, this landscape into sub-landscape types. This is less important in some modeling. I don't want to say importance because it really depends on what you're doing. Less known than slope and aspect. Now, TRI, Topographic Ruggedness Index, and roughness are basically the same thing. So if you look at the maps, you're not going to see much difference. Maybe a little bit. But they are measured in different scales. This one's measured to maybe 180. This one's measured to, looks like about 450. They're just computing on different scales. But essentially what they do is they're the degree of irregularity of a surface. So it's calculated by using the largest intercell difference of a central pixel and its surrounding cell. Basically, it's saying how much does one pixel vary from the surrounding pixels in terms of elevation. So it's computing the ruggedness of a landscape. You can see our darker values for both of them, and even getting into the greens, are our roughest terrain. So it's going from, really flat surfaces to high elevations. So you may get a solid cliff, but oftentimes you have a few cliffs, and so it's pretty rugged terrain. It's pretty irregular between cells, and so this is just measuring the roughness of the landscape. Higher the value, rougher the landscape, and you can think about that as having a lot of geology, a lot of different slope faces, a lot of degrees of slope that differ between the surrounding cells. Now, roughness, one use that I know of, it's very helpful in habitat suitability models of some birds that prefer cliffs and mountain lions and ambush predators. Mountain lions like rough terrain. You can see where even just looking at some of these areas, you would be less likely to encounter a mountain lion than some of the other ones. And that's just one opinion. But great. We started with one digital elevation model that was computed from two, right? We cropped it down to our landscape size, Zion National Park. We have run a few different analyses on it and created a few different products. That's great. We could plot them all separately. We could either do the par MF row equals C, do, 1 by 5. We could have 5 plots in one row if we like to, and we could save them all as individual rasters. However, raster data has the unique option of being stacked. If 2 or more rasters have the same extent, coordinate reference system, and resolution, and guess what? They don't even need to be the same resolution. I lied. They just need to be the same extent and CRS. They can be stacked on top of each other and act as a single TIFF file of multiple layers. So they have all the same extent. You could essentially just say, I have a raster data set that has 5 layers. It has my slope, my aspect, my TPI, my TRA, and roughness. So we'll see what that looks like. It's pretty easy to do. I'm going to call it rasters with a Z, 1 because I like putting Z's where S's should go, and 2 for Zion National Park. So how to stack rasters is just using the concatenate function. So C, parentheses. And we're just going to put in our rasters that share that same CRS and extent. So Zion M, our digital elevation model, slope, aspect, topographic position index, topographic roughness, ruggedness index, and roughness. And we're going to save them as rasters. So how does that look in the descriptive output? You can see that we are working with spat rasters as the class, and the dimensions are 1,601 cells by 985 cells for rows and columns. And then it goes into number of layers, 6. How many rasters do we have? 1, 2, 3, 4, 5, 6. 6 rasters. So we now have one spat raster that has these 6 layers, and you can even get into the names. Zion A, which is technically the name of our digital elevation model, slope, aspect, TPI, TRI, and roughness. And then it will give sort of a characteristic of what they have. You have the coordinate reference system. You have the extents in meters. You have the resolution. And so while it's 30 meters, technically it's saying they are actually 27.9354 meters in resolution, so their length and width. So that's really awesome. Now what happens if we just look at the dimensions? You will see the cells by the cell count and then the number of layers for a raster stack. And then what happens if you plot it? If you just run teraplot rasters with a Z, you will get 1, 2, 3, 4, 5, 6 rasters. Excellent. This is a great way to save your raster data. And it's a great way. You could just do teraplot rasters and then do the $sign and pick a specific raster you want to plot, or you just plot the whole thing. So it's a neat way of kind of organizing what you're doing, because you could save all these as separate rasters, but that just gets messy after a while. Now, if you've ever taken a physical geology or geography course or ever looked at a map, chances are you've come across contour lines. Contour lines that continually cross a single unit, are lines that continually cross a single unit of elevation. If contour lines are close together on a map, count on steep terrain. If they are widespread, the terrain should be gentle slopes. Now, contours are just an excellent visualization of how the elevation works in your landscape. And it runs as such. We're plotting teraplot Zion M, which is our digital elevation model. Then we're going to run the contour function. So contour is quite easy. Just going off of the default settings, all you do inside of contour is put in your digital elevation model and run add. And then I plotted the Zion boundary around the inside. But that's as simple as it can get. You run the contour function, digital elevation model, and using the, what's that word? The default settings, and you add it, this is what you get. And you can kind of see how there are some numbers in here. So this is the elevation of 1400. Up here you have 1800. You have 2400 up here. You can get an idea of how the topography of the landscape is looking based upon contour lines. Now, you can actually choose how many contour lines. So this looks pretty messy. I think the default is 10 contour lines. So if this was a larger landscape, 10 might not be so overwhelming, but right now it is looking pretty wild. I like it, but pretty wild. So if you don't like the distance between the lines, you can change that by inside the contour function using n levels equals. So we're going to give it 5 contours. So what does that look like? 1, we plot our digital elevation model. We're just going to call it 5 contours. Then we'd run the contour function, and we're doing Zion M, right, a digital elevation model, add equals true, n levels equals 5, and then we're plotting the boundary around it. So now we only have 5 contour levels, starting at, looks like 1500, then it goes up to 2000, and such. Pretty neat stuff. Contours are a great way for visualizing your data and making the most out of your maps. Now, sometimes we're working with rasters that come with these predefined values, and we want to reclassify them. So if you want to do that, you will use the classify function. So classify allows you to reclassify the values of a given raster. For example, our digital elevation model right here, ta-da, ranges in elevations from around 1100 meters to 2650. So any value between those two could occupy a given cell within that raster, if that makes sense. Reclassifying a raster would allow us to say any value between 10,000 and 1500 meters in elevation will now have the same pixel value. So class 1 in a sense. We're really just breaking down all the potential values of the digital elevation model or whatever raster you're working with. We are breaking down the values of a given raster into categories. So let's take a look at how, first let's take a look at the output. This is a digital elevation model reclassified, but with only 4 classes. So in kind of our salmon color here, we have all elevations that range from 1,000 to 1,500. In our yellow, we have all values that are 1,500 to 2,000. In our light greens, we have all values from 2,000 to 500 meters. 2,000 to 200. 2,000 to 2,500 meters. And in our darkest green up here, it looks like we're having values that are in 2,500 meters to 3,000 meters. Great. It's just reclassified. So how does that look? This is just our Zion M. It's useful to run just the raster you want to reclassify first so you can get a look at the values, min value, max value. This is how you run the code. So I'm calling it classifies just for funs. So Terra classifies the function. First you run the raster you're interested in working with. For us it's Zion M, our digital elevation model. And then we want to have the following categories: 1,000, 1,500, 2,000, 2,500, 3,000. So I know what you're saying, but we only had 4 category outputs. How do we have 5 values? So it starts with your minimum value, and goes to your maximum value. So our first class is going to be 1,000 to 1,500. Our second class is going to be 1,500 to 2,000. Our third class is going to be 2,000 to 2,500. Our fourth class is going to be 2,500 to 3,000. So our digital elevation model didn't even have values at 1,000 and 3,000. Doesn't matter. Whatever bound they're set at, it will count for those values of your raster. So 2,500 to 3,000, our data doesn't even go past 2,700 yet, just for continuity. I can put 3,000. Cells don't exist, so it doesn't matter. But it will go up to 3,000 if they were available. So you run the classifying function, and then you can plot it, and I'm putting the boundaries, and check it out. Beautiful. I think that this has their... Some habitat suitability models don't run on a specific algorithm, but of a weighted mean average. And so let's say you're interested in bighorn sheep habitat. You're probably going to reclassify a DEM to include higher elevations. But then what about slope and aspect? So getting into slope and roughness too. You'll see that bighorn sheep, they're generally on rougher terrain, high elevations, steep slopes. You can run a weighted mean average to get kind of the best suitable habitat across a landscape just by averaging those values. And so reclassifying has its helps. You'd want to reclassify that to the steeper slopes, to the more rugged terrain, and to the higher elevations, if you're looking at bighorn sheep, for example. But we're not going to really cover weighted mean averages. We're going to get into some statistical algorithms for species distribution modeling later in this semester. But for right now, you know how to reclassify data. Great. So let's say now we are working with the National Park Service, and they want to create a table of all the scenic overlook points. So their location, and then at what elevation they occur. So we're going to be using extract for that. And extract does exactly what it sounds like. It extracts information. A very common practice in spatial modeling, particular species distribution modeling, requires a data set of points. We'll get into what these points are. And these points that contain the value of many raster data it overlaps with. For example, load into your script the overlook shapefile. And so that's from the data. And these are designated scenic overlooks in Zion. And so we will load them in. Perfect. Now, since when you are working with AEA N83, we are going to transform our overlook shapefile, right? We're going to be plotting our DEM, plotting the Zion boundary, and plotting those overlook points. So right now we have our digital elevation model, and we have some point data of the scenic overlooks, right? Now those point data, spatially they're associated with a value in our digital elevation model, but that value isn't included in their own data. It's not included in the column in that point table. So extract will help us do that. So now overlook points do not have information regarding DEM, like I just said, but in space they're synonymous with an associated elevation, like I just said. Extract can take point data and extract those associated values of a raster or a polygon. You can use polygons for this instead of a raster. Now let's give it a test run and see the output for extracting values of our DEM to our points. So, one thing that you need to do first is now transform it to a spat vector. This function requires the vector data to not just be SF because it doesn't work with SF. It requires them to be spat vectors. So using our as function, once again, we're going to be calling this overlook underscore v and assigning it to the as overlook or shapefile and calling it a spat vector. Perfect. Now we can move forward. Calling a new variable overlook underscore ex, so for extract, we're going to be using the extract function from the Terra package, extract. Zion, our digital elevation model in this case, and our overlook v, overlook v, which is our points of observation, our scenic overlook points. So running through extract, we're taking these points, this raster, and we're taking the values of this raster and putting them as a column in our overlook. So now let's see what that looks like. So technically, we've named our digital elevation model Zion, but it's really called Zion A in its data. But these are the points, the top 6 points, 1, 2, 3, 4, 5, 6, and these are the associated elevations of those points. So maybe point 1 is down here, it's at 1864. Another point's up here, it's at an elevation of 1677. Up here is maybe a different point, and it's at 2382. It's just taking the values of the specific raster and making them a column in that point data. Now, remember when we did our little stacking? We don't need to extract by each single one if we wanted the extracted values to our points here. We can run it on our stacked data, our rasters with a Z. It's the same idea. You already did this, you technically don't need to run it again. I must have run it twice. But we have overlook underscore ex is Terra extract, and we're doing our raster something is wrong here. Alright, there we go. Overlook underscore ex Terra extract, but instead of just using our DEM, we're using rasters, our 6 stacked rasters, and we're doing overlook v, our spat vector of points. So check it out. Instead of just having our digital elevation model values, we now have our digital elevation, slope, aspect, TPI, TRA, and roughness. So now each one of these scenic observation overlooks has a column that ties directly to 6 different raster data. So you can get a good idea maybe which ones are easier to get to. Maybe which ones will give you the best scenic overlook in terms of elevation and what you can see on the landscape. Maybe you want one that's really back in the rocks, maybe somewhat rough, harder hike to get to. 44, that's a higher roughness value than the other ones. So maybe you want one on a really steep cliff. 5 is going to be steeper than, say, 3. So this gives you information into the landscape characteristics of each observation. And so this can be used for a number of things. In species distribution modeling, we're going to be using species occurrences. So observed reports of a particular species. But we're going to be using like slope, aspect, elevation. But then we're going to be, if we're working with trees or plants, we're going to want to know soil characteristics. And then we're going to want to be looking at climate, because climate is a large factor in the distribution of species. So this is a really important process to understand. It's actually a pretty simple way to do it. You just use the extract function, provide the raster or rasters, and then your point data, and you extract. And perfect. You want to recreate the style of these tables. These are nicely looking. Install the pander library, then using the function pander, put in your points, or whatever you'd like to look as a table. Pander just creates nicer looking tables. Perfect. So our raster data came to you pre-wrapped package. This is a great little raster data. Feel free to use it. But what if you have polygons of some data and you can't find its raster equivalent? Well, if that's you, then look no further. Rasterize allows you to rasterize polygons. It requires you to have 2 things. 1, a polygon to rasterize, and 2, a raster data set that it can call the coordinate system and spatial resolution to match. So the polygon will be rasterized and will match the same CRS and resolution as the provided raster, as I just said. In the data folder, I have provided a shapefile called soil. Load it into your script and let's take a look. Perfect. stread, just like you learned in week 4, and we're loading that in and calling it soils. It has 13 features and 59 fields. So there are 13 specific polygons within Zion National Park across 59 fields. So there's a lot of soil characteristics in this one shapefile. We want to work with just rasterizing one of them, but this is its geometry. So let's look at what's going on inside of this soils shapefile. So we have a lot going on. We have some helpful fields and some maybe not so helpful, but some of the more helpful ones in maybe vegetation studies: pH minimum, pH average, pH maximum, fragments from 3 to 5 centimeters, sieves number 4, 10, 40, 200, percentage of sand, silt, clay, OMR. What does that stand for again? Something. Is anyone here a soil scientist? I don't even know why I asked. You're not here. Dry weight, potassium saturation, average water content, water saturation, things like that. So this has a lot of information about soils. I want to create a raster of one of them through its polygon values. I'm just going to create one from pH minimum. So I want to create a raster of just this going on. So how do I do that? Using the rasterize function. So this data is already trimmed to the Zion National Park and contains a lot of fields, as we just spent like a minute talking about. And as you recall, a shapefile can contain one geometry but multiple characteristics. Once again, we just talked about that. Let's rasterize this thing. Syntax goes as follows. You'll call a variable. You'll do the function rasterize, and you will have that specific polygon you want to rasterize. You will have a raster of a particular CRS and resolution that you want that polygon to mimic in terms of CRS and resolution. And then you will run the field equals, and in quotations you will put which column do you want to rasterize. For us it was pH min, pH minimum. Let's see how that looks. So, turning our soils into a spatial vector, one thing you must do, it cannot work with SF objects, needs a spatial vector. So now we have soils underscore v, a spat vector of the soil geometry and all of its characteristics, and we're going to create a new one called pH average, although it should be pH minimum. This was a mistake. Just pretend it's pH minimum. So we're going to be running the rasterize tool function. So we're running soils v, our spat vector of the soils polygon. Zion m, that's our digital elevation model. It contains a specific CRS and a spatial resolution, so 27 point something meters of a spatial resolution. And then we want to rasterize the field pH min. We're going to plot pH average, which should be pH min, but check it out. You now have a rasterized polygon, or rasterized polygon of the pH minimum of the soils. Great. And they have a specific value tied to them. This raster acts just like any of the rasters you've seen before. It was just created from a polygon. So while it may look a bit more blocky, that's just from the geometry and values that we're coming from. Because soil science, is this perfect model of reality? No. But measuring and monitoring soils across landscapes is extremely difficult. And this is actually pretty good if you want to work with soil data as a raster type. So great, now you know how to take polygons and make them rasters. One last thing to cover, well, I guess a couple of things, but one big thing to cover is raster math. Now, rasters of equal extent and resolution and coordinate system can use mathematical function, those mathematical operators, plus, minus, divide, multiply. They can use those functions to generate new rasters of the same spatial characteristics. So we can take two rasters that are equal in extent, resolution, multiply them, add them, divide them, subtract them from each other, and create a new raster, just using those mathematical operations, because each cell has a value in it. And we can use equations to see difference between cells over time, things like that. So I have provided two raster data at 1 kilometer. You can see they're far more coarse than the the data up here, right? 27 meters in resolution versus 1 kilometer. You can still get the idea and the shape of the landscape, just far more coarser. So, far more coarse, whatever. So, the one on the left is the 30-year average of annual mean temperature. So each cell, that's the annual mean temperature in Celsius, not degrees. Sign is not that cold. Then on the right, we have a projected, so into the future, average of what would be 2071 and 2100 30-year average. So while these two rasters may look the same, look at the scale bars on the right of each plot. 2100 is showing much higher values of annual mean temperature, whereas current temperatures are just not as hot or as warm as the future prediction under a specific emissions scenario. We're not going to cover what that is. Just know that this is projected to be 100 years in the future. Right now, 78 years in the future. So let's say it's warming in 2100, right? And I have our current. So what I want to do is I want to subtract these values from these values. So if there's a difference, the value will be negative, but I'll be able to see by how much, in a sense of how much warmer is it getting. I can run a really, really simple function. So I'm just going to call it x, and I've loaded these in, and I've called them clim. It's a raster stack, and it has both of these in it. So I want to take the first one. I'm going to do clim, then I'm going to do my $sign, and I'm going to select the 1981 to 2010 30-year mean average, and that's the name of it. All I have to do is put the $sign, the rest can populate for me, and I just select. Now, I want to subtract it. It's hard to see, but there's my subtraction, my minus sign. Then I'm doing clim, the raster stack, I'm doing the $sign, and I'm calling the second raster. So the average of a projected 2071 to 2100. So I'm just subtracting this one from this one. I want to see if there's any change, and check it out. After running that little equation, I can plot x, and this is the value. So raster cells that do not have any coloring or information means that there was no change. So, minus, I'm getting 0. However, the higher it goes, lower, so again, these lower values, so yellow, and we have some of these kind of darker yellow colors. These cells are undergoing significant change. So, in a sense of subtracting them, they do become negative, but now I know that there's a difference between these cells of about 4.5 degrees Celsius. That's a lot going on. Whereas up here in the higher elevations, maybe there is change, but it's not as extreme. Extreme is the wrong word for it, because 4.4 to 4.5, that's both pretty crazy. But the example is not necessarily about climate. It is that you can use mathematical functions to create equations and evaluate change or any type of variable you really want to create just by using mathematical functions. So, pretty cool. Now, you have worked with a lot of raster data, right? If you exited out of R and didn't save your stuff, it's gone forever. You'd have to run everything over again. Now, you can save these rasters, whether you want to save them singularly or you want to save them as a stack. You can use the write raster function. So write raster function is really easy. Make sure you are using the Terra package to do so, but it's write raster, capitalized R. You will include the raster name that it is saved in your R script or R studio. Then you will do file name equals, and in quotation marks you'll put your pathway, and then to the folder that you want to save it in, and then you'll give it a name and .tiff. And you run that, and it's as easy as that. You have now a saved raster. If you save a stack and load it back in, it could look like this, where you're just loading one variable, one tiff, and you're getting 2 or more rasters. So pretty cool. Now, your assignment is going to require you to find some of your own raster data. I've put a couple links to get you started, or you can just go on Google and type in raster GIS data, whatever you want. Maybe you're looking at Yellowstone, so Yellowstone National Park raster GIS data, or Yellowstone raster GIS download, something like that. Just be careful of where you're searching online. Sometimes there are sketchy websites. You never know what you're downloading into your computer, so be careful. But I've provided a few here. The National Map Downloader is a very, very common one to use. It's great. So let me go to it. All right, there we go. National Map Downloader. So this is from the USGS, and look, a national map. This is just a way to get data pretty easily from the government on certain areas. And so let's say I'm still interested in Zion National Park, so I am going to come down here. And after looking at Zion National Park, I should have a pretty good idea of what it looks like. This is just embarrassing. Gosh, I'm so embarrassed. Okay, Hurricane, Laverkin, Hurricane and Laverkin. Great places. um, Gotcha. Oh my gosh, I can't even find it. So much for being my favorite national park. Anyways, let's say I just want to collect some data in here. I'm pretty sure this is Zion National Park. It's just not giving me that area. Yeah, because Penguich is up there. Anyways, you can create an extent of the data you'd like to collect. So let's say I want to collect data just here of the North Fork of the Virgin River. I could come in and hit Polygon over here, and then click, 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 clack, and then double click, and it will save that boundary, right? Now I can come in here to search products and look down. Let's say I want to collect a digital elevation model of this area. I would go to elevation, and it will give me certain characteristics. So there's 1 arc second. An arc second is 30-meter resolution. Then there's 1 meter resolution. That's pretty dang good. 1/3 arc second. So 1/3, so about 10-meter resolution. 1/9 of 30 meters. A 60-meter resolution. 5-meter resolution for Alaska only. Interesting. Let's say I want to collect 1 meter resolution of this area. I would select it, and then I can go to search products. Check it out. Now this is a pretty big extent, but you can add in, say, look, this digital elevation model here. Let's take a look at it. So that is the extent is 10,000 meters by 10,000 meters. So that is a 10 kilometer by 10 kilometer extent of a digital elevation model made up of 1 meter cells. Or what did I select? 30-meter cells, something like that. But then after you hit footprint, you can go to download TIFF, and it will take you, and it will download right into your computer. I technically don't want it, so I'm just going to stop that. But that's an easy way to access data. So that's one option. Where is, all right, check it out. Natural Earth data. Let's check this one out. Natural Earth provides information about the natural Earth. So if you'd like to download stuff, you can hit raster data from large scale, medium scale, small scale stuff. I want raster data for medium scale. So it's going to take me to a little data depository and see what they have. Great. Here's a lot of stuff about, digital elevation. You can get shaded relief, ocean water, drainages with lakes. And what's interesting about this is that it's not specific to the United States, like the USGS is, but this is the natural Earth. You can get information around the Earth. Now, free GIS data library. It should be data library. This link is pretty awesome. So, R.T. Wilson, whoever this individual is, has created, and they're updating it too. This list was updated on 2 February 2021, so just a couple days ago. That's awesome. So they have created these general topics and are giving you links to data to collect. So physical geography, general, land, elevation models, weather and climate, hydrology, snow, ice, natural disasters, land cover, ecology, mineral resources, and then you can get into human geography, administrative boundaries, environmental boundaries, land use, wars and conflict and crime, population, individual country area data sets. So RT Wilson, whoever they are, thank you for everything you're doing. They are just providing a library of places to search. They do have this beware, which I've told you, some of them may be inaccurate, incomplete, or wrong. Be careful of what you're using. Be careful of what you're going to, but generally everything in here should be fine to look at. So I would say this is something you should bookmark, hold on to. It contains a categorized list of links to over 500 sites that are freely available geographic data sets, some vectors, some raster, some imagery explicit data. So very awesome stuff. I encourage you to take a look through those as you go through your own assignment. But for now, we have covered a lot of the basics of raster data, how to use it in 70 minutes, which is longer than anyone should ever be talking or listening to me. So good luck on the week's assignment. It's a lot like week 4. You have a lot of creative control in what you'd like to do, except for that you'll be specifically bounded to a park boundary of the National Park Service. So have fun. If you have any questions, please email me. We can set up a Zoom if you'd like. Just try to stay on top of your work. The semester goes by fast, but so far everyone's doing great. And have a great week 5.